Welcome back, class. The intent of this video, I'm recording it outside of normal times, is to make up for our first night of the op amp when we experienced some technical difficulties with setting up the webcam. I still haven't found a good way to go about working forward with a webcam right now. I think it might be good for pointing out a few quick things, but in the interest of showing you how to connect everything, I found it's better just take some screenshots, pictures, and kind of draft up some slides for you. So tonight, I'm going to walk through this deck, show you the table of contents here. We're going to discuss how to connect a circuit on a proto board, connecting the analog discovery 2, setting the bias conditions, then fix that real quick. And performing some measurements, basic measurements. Now, the intention of this video is not to be completely capture every single step that you're going to do in terms of measurements. Some of that you're going to have to do on your own. If you run into difficulties, that's what office hours are for in our next lab session. And I'll make sure I'm available to answer those. Just real quick, I want to point out that the Zoom link, which was recorded on September 24th, the previous full session, covered the hand calculations and the P-Spice simulations. So let's see. All right, let's get started. First thing, proto board basics. Prior to jumping in how to connect the circuit, I just wanted to discuss some of the continuity features on the breadboards, also known as proto boards. So the first one we're going to discuss is the power rails. You'll notice at the top and bottom of the breadboard, there are two distinct rows, each labeled with a negative and a positive. These are continuous in terms of continuity all the way across the row. So each of these dots connects all the way to the very end. So for example, in this lab, one proposed method might be to use the top one here for your negative 5-volt supply. Then the bottom one here, the red line going all the way across, is your positive 5-volt supply. Now, what do I mean by continuity and all the way across? Well, if you had to tap off to multiple points for 5 volts, say if you had a circuit here, you could tap off here, then here, you could tap off here, and so forth. So every one of these dots along this row are all connected to that 5-volt supply. And the same thing for the blue line. They're all connected to the negative 5-volt supply. Now, I just refer to this general area right here in the middle as your proto or your development space. So I've dropped in a block representation of our 741 op amp. It has 8 pins. And what I'm showing here is that this area is not the same as the power supplies. The difference is now the columns have continuity all the way down, with the exception you have this break in the middle right here that I said there's a discontinuity. So for example, you have column 1 will be connected for rows F, G, H, I, and J. Then down here, it'd be A, B, C, D, and E. So another way to represent this, I went out to column 27 here, this green line. So all these dots coming down to this pin on the op amp, they're all connected to the same, we'd refer to it as net. So if you could have multiple components tie into this pin right here on this op amp, and they'd be all connected together on this green line. Same thing down here. This yellow line, this particular column right here, they're all connected together. All right, so let's work our way towards building up the circuit. Prior to jumping into the circuit, we'll talk quickly about the device that we're going to put on the board. This is our DUT, device under test, is the LM741 op amp. It's an 8-pin DIP or dual inline package. So you have 2 rows 4 pins. So this is what the actual device looks like. Then here's a pinout diagram for the LM741. They give you a notch in the top, which is represented right over here, to give you an indicator as to where's pin 1. Then they give you the numbering order going around the device through pin 8. You might ask, what's NC? NC is just no connect. It's an unused pin, but it's still present for mechanical stability. Let's see, what else do we have? We have 2 input pins, right? So this one's a really nice pictorial of the op amp, because you have the op amp symbol. You can see the inverting terminal, which is pin 2. You can see the non-inverting input, which is pin 3. Then we have 1 output, which comes out of the op amp to pin 6. We have 2 supplies. So pin 7 is a V positive. Then pin 4 is a V negative. You can operate this op amp 2 different ways. This lab will be doing it as a dual supply. So we're going to have a positive 5 volt and a negative 5 volt. And the next lab, which is the single supply op amp lab, you'll be operating it as a positive 5 volt on 7, but you'll have pin 4 at ground. Let's see, then there's 2 offset null pins. As we discussed in the previous lecture, not all op amps come perfectly balanced in terms of if the 2 inputs equal each other. With a positive 5 volt and negative 5 volt supply, you'd expect the output to be at 0 volts. So right in the middle, those 2 supplies. If there's an imbalance, that's referred as an offset, and maybe the output is, 5 millivolts. It's going to be gain dependent. You'll learn more about that. So there is a way to correct that. If the factory condition of the op amp is not sufficient for your application, I've shown it down here. This is a additional peripheral circuit you can use to nullify the offset voltage using a resistor between pins 1 and 5, your offset nulls, with a potentiometer. So this is a schematic symbol for a potentiometer, which is an adjustable resistor, 3-terminal. So again, this is just for your reference. Let's see, what else? The last thing. I always highly recommend anytime you use a device that you go to the data sheet. So I provided a link here. The data sheet's going to provide you with typical operating conditions, maximum operating conditions. So what's the largest supply you could use, largest input voltage. It's going to tell you things like possibly what's the open loop gain for this op amp, what's the maximum operating frequency, things of that nature. All right. Moving on to the next. So for this lab, you're going to be connecting the circuit up in 2 different configurations. The first one is the non-inverting amplifier, and the second one is the inverting amplifier. The key difference, which we discussed in the previous lecture, so I'm not going to go into a lot of detail here, but on the non-inverting, you're applying the input to the non-inverting pin, and on the inverting, you're applying it through a resistor to the, which is part of the feedback network, to the inverting pin on the op amp. All right, how do we connect all this together? Let's go to the next screen. Let's see, I'm only showing this picture because I didn't think there was too much benefit, but maybe just enough for this one. So let's start off. We have the proto board. I've taken the pinout diagram of the op amp and rotated it, plugged it in virtually to my proto board here. And I put down my RA, my RB, and now we're going to connect it all together. Let's start off with the power first. So my negative 5 volt supply will be right here. So I'm just going to jumper that over to this pin. And that's what the dots represent, is a wire going from point A to point B, if you want to call it that. So I got a wire going from here to here, which is putting the negative 5 volts on pin 4. Then the red one, we have a wire going from the positive 5 volt supply rail to here, and that's putting 5 volts on pin 7. Our input is going to pin 3, the not inverting input. So I just got, you know, a yellow wire tagged into that pin right there. Then this end will be connected to your function generator. Then we have our feedback loop. So we're going to go from the output through RB to the inverting pin. So that's pin 6 to pin 2. So we're going to come over here. We got pin 6 on the output. We're going to connect the resistor to pin 2. Then from pin 2 to ground, we have RA. So we got pin 2 through RA to ground. Now it might be a little hard to see in my picture, but I still want to include it just to show you how you can save some wires. So for example, here's my RB going right across the op amp directly from pin 6 to pin 2. Then from pin 2, I got my resistor going from here to this point, in which I have a jumper, this black wire, that takes it up to my ground rail. Let's see, that's that extra negative rail up here. I'm using that one as my ground. So that's my ground wire right there, which represents this part of the schematic. My supplies. So I'm going from pin 7 to the 5-volt rail. So that's this wire. Then my negative supply, I'm going from pin 4 to ground. So that's from here to here. That's my negative 5-volt supply. So from here to here. Then my pin 3, would that be my input? That's my yellow wire coming off right there. Let's see here. I didn't include a picture for this one, but you get the general idea. Same thing. The key difference here, it's this almost identical configuration to the previous one. The difference is now you want pin 3 to go to ground. So that's your non-inverting input going to ground. And instead of RA going to ground on this side, RA is going to go to your function generator. So you still have RB going across from pin 2 to pin 6, and the power supply rails are still hooked up. And this side of RB on both schematics, which I didn't point out on the previous one, is your output voltage, pin 6. All right. So let's talk about the analog discovery really quick here a little bit. I went through mine and they provide you with this nice packet of labels. I've already pulled the first one off here and attached them to all the wires that I'm going to be using in this lab. Now there's definitely more included than you need. If you want to put them all on, by all means, connect them all up. So what I did was I took this sheet and I used this reference diagram that's part of your kit. And you can see like 1 plus is scope channel 1 positive, 2 plus, which would be this sticker right here, is scope channel 2 positive, and so forth. So I did from here through trigger on the top, and from scope channel 1 negative to trigger on the bottom, and labeled all these wires up. Then I took the remainder of these digital I/O signals on top and bottom, and I just zip tied them underneath the pucks since I'm not going to be using them. You can see those wires folded under. Then the top group right here, I zip tied those together right here. Then the bottom group, I zip tied those together right here, just to make it a little easier to keep track of everything. And you can see what labels I use based off of this. What's the next thing? Components. So your Analog Discovery 2 came with a rather lengthy inventory of components. I've mailed out the 741 op amps. Everyone should be receiving them in the mail today. And I also included a bunch of 10 microfarad capacitors that will be used in subsequent labs. So I wouldn't worry about the ICs. You're not going to need it for this lab and the next lab. We're going to use the 741 op amps. And don't worry about any of these devices. But what you are going to need is resistors. So here's all the resistors that they provide you. And they tell you the quantity, the value, at least the nominal value. Remember, there's going to be some variation. Then they tell you these 3 bands, right? You're like, oh, what are these 3 bands? What do they represent? On the inside of this lid, you get this nice little chart here. And what the bands tell you is you actually have 4 bands. They just disregard the 4th one, which is the tolerance. I didn't look at it. They might all be the same tolerance, to be honest. Gold, which is plus or minus 5%. I think some of them are gold. But anyways, you're going to want to refer to the first 3 bands. You have 4 band resistors, and the colors, the first band, will tell you, here's a little mapping chart for number to color, or you could just come over here and know that these are the first 3 bands that you're looking for. And if you see brown, 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 you know that's a 1.1 ohm resistor. If you see yellow, purple, red, that's a 4.7 kilo ohm resistor. So unfortunately, with these analog discovery 2s, you don't have the option to measure impedance with them, at least that I've seen. I think it's an additional module. I got to play around with it a little bit more. I'll let you find out if I have a technique for doing it. The other option, if you happen to have one at home, or if you go to like a Harbor Freight Tools, you could get a multimeter, which honestly I highly recommend. It'll make troubleshooting a little easier. And a multimeter will permit you to perform voltage, current, and impedance measurements on your circuit. And you can pick a really cheap one up for like 10 bucks at like Harbor Freight. Let's see here. Now I just want to say that the multimeter, it's not required. I'm just recommending it as something that could potentially make it a little bit easier for you to perform some of these labs. All right. So now how do we connect all this together? So we got our circuit and we got all these wires here that go to our analog discovery puck, right? So I went through and I labeled them all. So you got your ground, which is going to connect. So I'm going to use like this ground right here, right? This black one. And I'm going to connect it. And actually, I take that back. You don't need these 2. I'm going to remove that. So I'm going to connect the ground to this wire. I'm going to connect my V positive to this wire. I'm going to connect my V negative to this wire, my function generator to my input. I'm also going to include my scope channel 1 on this because I want to look at what's going into my circuit, right? What's being applied to it. And lastly, I want to look at what's coming out of it, my scope channel 2 on the output right here. Now, I'm going to walk you through right now using waveforms. I have this very circuit built up, but with slightly different resistor values. So just for your reference, for the resistor values, RB, I use 10K, and for RA, I use 4.7. I'm not sure if those are within the tolerances of the lab instructions. I believe they might be slightly outside for RA. So again, I just arbitrarily picked 2 values for this lab. So with those 2 resistor values and the non-inverting configuration, that gives me a gain of 3.12. Now that's what I expect if both resistors perfectly match, right? Like, you know, if RB is perfectly a 10K and if RA is perfectly a 4.7K. In the real world, again, remember that gold band, the 4th one, the plus or minus 5%? That's the tolerance. That's where you're going to have variability. And that number, your gain number, will be slightly different. Let's see. The next slide is troubleshooting. Let's talk about troubleshooting really quick before we hook everything up. So fundamentally, why do we do troubleshooting? Well, things don't always work as planned. Some of you are going to hook the circuit up. You're going to go through the waveform steps, and you're not going to get the output that you anticipate. Now, I say anticipate because hopefully you already have a thought of what you expect the output to be based on your knowledge of the circuit. Again, if you hook it all up and you just look at the output without expectation, how do you know if it's right or if it's wrong? So again, put some thought into what you expect. For example, this is a gain circuit, right? So if you're looking at the output and comparing it to the input, you'd expect possibly, well, let's be honest, okay, for the non-inverting configuration, you'd expect the output to be a gain version of the input, right? So what are a couple things that could happen? Well, let's just say the output is bad. Let's go through this. What I recommend performing is a divide and conquer approach. You want to fundamentally figure out what's not connected right within your circuit, because it's going to be one of a possible couple things. It's going to be either your circuit's not connected right, your waveform measurement isn't configured right, or possibly there's a faulty component in your circuit. The most likely of the three is something's not connected right. The next likely is you're not applying the correct waveform settings. Well, so when I say waveform settings, I'm referring to how you bias your circuit and control it. So how then the last thing is a bad component, which I've provided everyone with 3 op amps. So just swap the op amp out. All right, so if your circuit doesn't work, how are you going to check it? Well, here's what I would do. Let's just assume the output's bad. We're looking at the output with the oscope channel 2, and it's just flat, right? And I'd recommend with oscope channel 1, as we had it configured on the previous schematic, you check the input. You're looking at the input, right? Hey, input looks great. I'm seeing a sine wave as expected. All right, well, I know I got a good signal coming into my circuit, but something's not great coming out. What should I check next? So take your channel 2 of your oscope, because that's going to measure time varying signals, but you can also do DC measurements with it too and see shifts, right? So check your supplies first. Do you have positive 5 volts on pin 7? Do you have negative 5 volts on pin 4? If you don't, correct it. If you do, move on to the next step. Check the bias point at the intermediate node. So when you check the bias point at this point, I recommend you turn off the function generator, because you don't want a time varying signal going into it. You just want to look at the DC voltages at some of the intermediate nodes. Use your oscope to probe around with a wire and plug it in at the appropriate points and see if something's working. All right, I'm going to go to waveforms now. Got my circuit hooked up here. I'm going to launch my analog discovery 2, and I'm going to walk through this just a simple configuration. So the first thing I want to do is supplies. So I'm going to click on supplies. I'm going to do a 5 volt for positive supply. I'm going to click tracking, because I want the positive supply and the negative supply to track each other, just for one to be negative. So that's why I did that. I'm going to turn the system monitor on just for out of curiosity, see how the current changes going into the circuit. Really looks like they just provide you with the USB current coming into the puck. I'm not sure if that'll be of much help. All right, so the last thing, we got this configured, right? 5 volts, negative 5 volts. We got to turn it on. So here's the master enable is currently off. I'm going to turn that on. So now we're up and running, right? So the next thing, I'm going to come over to welcome, click on that, and I'm going to go to WaveGen. I'm just going to leave this at what it defaults to begin with, but let's walk through a few things. I'm going to leave it on sine wave, but you can do DC, square wave, triangle, ramp up, ramp down, and so forth. So for let's see here, DC, I wonder if you could do a sweep with this. Maybe. Or maybe just step through. That's another way to do a DC sweep with the test equipment. You just pick values, you step through them, and you write the values down on a table. So I'm going to leave this as sine wave. We're going to do it 1 kilohertz with a 1 volt amplitude. So again, I'm expecting a gain of approximately 3. So if I put a volt in, I'm going to expect about 3 volts out, right? I think it was actually like 3.12 was my gain. All right, I'm going to come up here and I'm going to click, you know what? I'll come back and click that. Let's set up our oscope first. So I'll come down here. I'm going to click scope. All right, so if you come over here to the far right, you got channel 1 and channel 2 selected. Both of them have an offset of 0 volts. So that's what this yellow caret right here indicates, that they're both referencing the 0 volt line. They both have a range of 500 millivolts per division. So that's that vertical value going up, right? So it'd be 5 volts, 500 millivolts, 1 volt, 1.5, 2, and so forth. So the y-axis are independent for each channel. They can have different values, but the x-axis is the time, and that's the same for both channels. So we're doing a millisecond per division. Keep in mind that the period of our signal is 1 millisecond. So we should be able to see multiple periods of the input and output, right, for this circuit. So I'm going to come back. We got our supplies on, double check. I'm going to go to my wave gen. I'm going to click run to turn that on. Now you can see it's running by this green box here. I'm going to go to my scope, and I'm going to do run from my scope. So run just means it's continuously collecting data, just 8,192 samples at a given rate. So the 800 kilohertz, I don't know if you recall from PSpice, where we did a transient simulation, we dialed in what the step size is. So that's the step size. They're just telling you, like, in what increment of frequency, you can do the reciprocal for time of how quickly this gets sampled, right? Then it's just showing you the recording of that data here. All right, so what do we see? We have channel 1 is my yellow. So I'm seeing a positive 1 volt peak. So that's in line with our wave gen. Let's go back to that. So 1 volt peak amplitude. So my input looks good. All right. Then my output looks like it's clipping right here, right? Oh man, is something wrong with it? Well, let's think about this. I got a gain of 3, so I expect my output to go up to 3 volts, right? Well, maybe it's not clipping. Maybe it's the screen's clipping because we don't have the range set correctly. So let's go back here to the range, and we'll set it at 1 volt per division. Ah, there we go. Now everything looks great, right? No clipping. So we got a nice output. Looks like our output is a gained up version of our input, but how much? Well, you can come in here and look at these lines and kind of get an estimate, right? Like it looks like 3.1, 3.2 over 1. So gain looks to be about right, 3.1, 3.2 area. Or we could come up here to this tab, measurements, click on that. You can go to add. We're going to do a define measurement. So we'll do channel 1, vertical. Let's do peak to peak. Oops, peak to peak. We'll click add. We'll go to channel 2, peak to peak. We'll hit add, and we'll close this out. All right, there we go. Now we can see it, right? So it looks like it got a gain of about 6.3 almost. I'm sorry, not gain. Peak to peak of 6.3, peak to peak of 2. So my gain is output over input. So 6.3 divided by 2 is 3.1. Hey, right on. That's right what we expected, right? Just about. Okay. So this is when everything's going right. Let's play around with it, see what happens and make things go wrong, just to kind of give you an idea. So I'm going to go to wave gen, and I'm going to turn the amplitude up to 2. So now we're doing 4 volts peak to peak, right? 2 volts up, negative 2 volts down. And I'm going to go to the scope. All right. So what happened? Well, now our input is going from, let's take a look here. Something doesn't look quite right. Let me change this. I'm going to change this guy to 1. Here we go. Okay, that's better. All right. So our input is going from positive 2 to negative 2. So that's our 2 volt peak that we set our function generator to, right? Come back here and double check. 2 volts, 2 volts. Now our gain of our circuit is, we'll just say approximately 3, right? So we'd expect the output to be 6 volts, correct? Are we getting a 6 volt output? Nah, it's capping off like a little over 4 volts, right? Why is that? Well, a couple of things. First of all, let's go back and talk about our supplies. Our supplies are limited to 5 volts and negative 5 volts. Those are our rails, right? Well, probably the first thing you're going to notice is, yeah, this is called clipping. So we're not getting a perfectly gained up version of the signal. It's going flat and it's limited by something, right? At the top and bottom. And it appears to be asymmetric because this one goes over 4 volts, but this one doesn't even reach negative 4 volts. So why is that? Well, that's why you go back and you look at your data sheet. Your data sheet's going to tell you that your op amp is only capable of reaching within a given voltage or fraction of the supply. And I say fraction because if you scaled this up to 10 volts, this would probably scale up by that fraction, possibly, and be within, you know, that percentage of the 10 volt. So this is clipping, and you're limited to the biasing conditions of the internal components of the op amp. We're not going to get into that, it's an advanced subject, but all you need to know is the way the circuits are set up on the inside of that op amp, that you can't reach all the way to the positive supply and all the way to the negative supply, and it's asymmetric. The positive supply you can get a little closer, the negative supply you can't get as close. So that's a good thing to know, right? If you're trying to center up your frequency, maybe on the output and achieve maximum signal swing, maybe you want to shift this up or maybe you want to shift it down depending on the conditions of the circuit you're working with. All right, so that is clipping. So I'm going to come back here. I'm going to change that to 1 volt. Now let's do another one here. I'm going to increase the frequency to a megahertz. So significant increase in frequency, right? I'm going to come back to the scope. Oh man, that looks horrible, right? What happened? Well, first of all, let's fix our time. You're seeing this blurred line going across the screen because we're doing a millivolt or 1 millisecond per division. What's our period of our signal? 1 microsecond. So this is like a significant period of time, right? Even within 1 millisecond, one period, or one major division here. So you're seeing like thousands of periods of that signal. So let's go down here and we're going to change it. Let's do 5 times so we can see 5 periods. All right. Actually, let's go a little bit lower. There we go. Okay. So now what are we seeing? Well, let's go back to our function generator real quick. So we're doing a 1 volt peak, and it's a 1 microsecond period for input signal. Let's go back to our scope here. And sorry about that, I just turned it off. So I have to click on it again. There we go, that's nice, it pulled it right back up. So we're seeing our 1 volt peak, and we're seeing a 1 microsecond period, and our output looks horrible, right? It's not even close. Like, not only does it is it not gained up, but it's not even a sine wave anymore. So what happened to our circuit? What's going on here? Well, here's what happened. Your op amp, as I'm sure you're learning about in lecture, has something called a fixed gain width band product. So what that means is that it is only capable of providing for a fixed feedback network a finite amount of gain within a finite amount of frequency. So what's happened? Well, we've exceeded that frequency, and as you exceed that frequency, your gain rolls off. So the gain of the circuit is substantially dropped off. And we're actually seeing some distortion now. We're seeing 2 things here. We're outside of the gain bandwidth product of our op amp for what it's configured for, and the op amp is likely hit a slew rate condition where the output can't keep up with the input. So I'm going to come back to supplies. We got wave gen. I'm going to crank this back to, say, 50 kilohertz. And we'll go back to the scope. And let's see here. There we go. Okay. So now we're starting to get a little closer back to where the op amp can operate, right? And I think this is a better representation of slew rate for you. So the input still looks great, but the output looks horrible, right? You have a sinusoid going in, and you have a triangle wave coming out. So why is that? Well, let's go back. Remember some of the non-idealities of an op amp that we talked about? One of them being it has a limited amount of current that the output pin, pin 6, can source or sync. So current, maybe it's a little bit more of a difficult way to think about it, but let's just apply our thought process here. What creates a voltage according to Ohm's law? So it's V equals I times R, right? So R is fixed, that's our resistor that we're dropping a voltage across, and I can change. Well, how fast can I change? Well, in order for this circuit to duplicate this sine wave, but in a gain version, right, on way up and down, it's got to be able to source and sync a lot of current really fast to create that gained up version of the input. So when that can occur, when the output hits a limit, much like the supply hits a rail, in this case, it hits a current rail on how much current it can source or sync, then you see a linear rise up and a linear fall down. So that's another one I just wanted to pick you up on, for you to pick up on right now. Let's see. I think at that point, that's good enough for tonight to conclude this session. I think the last thing I'll point out would be coming back to the function generator here. You can do DC inputs, which limits you to the offset. So I believe there might be one step where it asks you to do a DC sweep. So what you can do is come in here and start off at 0 volts, go to 1 volt. Then you can go look at your output using your oscope to see where it shifts. Let's do that real quick. I'm not sure why this isn't staying up. So for that, we could do a define measurement, channel 2, we could do the vertical, and we can do average, right? Hit add. We'll do channel 1, add, close. So what are we seeing? Channel 1, we have a 1 volt DC coming in. Channel 2, we have a 3.13 DC volt coming out. So that's just one way for you to go in and use a DC voltage to incrementally step through the entire range or perform a sweep and see what the values are. All right, I think that's going to conclude it for tonight. That should be sufficient to help you get started. So we covered up wiring the circuit up. Let's go back here, take a look. Circuit connectivity. So this is the one I walked you through, the non-inverting op amp, how to wire it all up. We talked about the waveforms, how to get your bias condition set, your function generator set, and how to use your oscope for transient and DC measurements. All right, let's talk lab report. Lab report. So for this lab, we'll have, let's see here, another lab night on this Thursday, so October 8th at 6 p.m. The lab report is due next week on 10/17 by 6 p.m. Everyone needs to submit it via Moodle individually. So what I want within that report is just show your hand calculations. You don't have to rewrite them, honestly. You can either scan them in or take a picture of them with your phone and embed them in a Word document. I would like to see a screenshot of your PSpice schematic, a screenshot of your simulation plots, a screenshot of your measured outputs, and you're going to answer conclusion items 1 through 3. And that's it for this lab report. If you have any additional questions, we can discuss them tomorrow during office hours, or we can discuss them Thursday during our next lab session. All right, that concludes tonight. I'm going to hit stop now. I'll convert this over. I'm going to post it on the Moodle page and send an email out to let everyone know it's available. And just take the remainder of this week between now and Thursday to perform these steps, set up your circuit, and complete steps 1 through 16. All right, have a great week.